it says use the graph of y equals 2 to the x. So what you're often going to do when you're graphing an exponential graph is the question would say, put this one in the blue box here. The question would say, can you graph this? The first thing you're going to do if you're asked to graph the thing in the blue box is to say, okay, what is my parent graph? What graph am I going to connect this to? And since the base of this one is 2, we're going to connect it to the graph of y equals 2 to the x. What does that look like? Well, it would have an asymptote at y equals 0. You would plug in the points 0, 1, and 1, 2. This is the shape of our base graph, and we want to graph the one in the blue box, which, boy, they don't start off with an easy one. They start off with one where you have to remember something from transformations. The special note about horizontal stretches, compressions, and reflections, and horizontal translations in the same question. Do you remember that if you have, so this is a 3 out in front times, we have a horizontal reflection because there's a negative with the x, and there's also a +2, so we have a horizontal translation. You need to write that in factored form. You'll be tempted to say that that +2 moves it 2 to the left. In reality, once it's factored, that moves it 2 to the right. One of the things and one of the reasons we don't do exponentials first in your transformations unit is the notation of an exponential function causes students to be a little bit more confused. Because in an exponential function, and I'm going to put a green box around the 2 and a green box around the x, because that is my parent function. But students are tempted to do something with the 2. The 2 is not a transformation. If we label our transformations from left to right here, we have a 3. That 3 is outside the function. That'll be a vertical stretch. That will multiply your y values by 3. The next thing we run into is the negative. That negative is inside the function. It's where the x was originally. That will be a horizontal reflection. You will multiply your x values by -1. And then the 2 is a horizontal translation. You will go to the right. Order of operations is really important. Your mental math skills will tempt you to break order of operation rules. You will see a question like this, and it will have 3 times 2. And your brain will tell you, you're good at this. 3 times 2 is 6. That's good that 3 times 2 is 6. But order of operations say you have to do exponents before you multiply. So you are not allowed to multiply the 3 times 2 and get 6 because you haven't actually done all of the exponents that are there, the negative, the x, the +2. In fact, we can't do them because one of them is a variable. So you are going to be tempted to multiply, but that is not allowed because it's not following order of operations. So there's the setup. We've got our graph of 2 to the x, our parent graph off to the side. We have to do our transformations, and for exponential functions, we're going to do it the same way that we did it back in our first unit in transformations. So a little review. What did we do in transformations? We listed our original points. I'll do them in green here. Then we drew arrows. And in our arrows, we always did our stretches and compressions first. So in this case, it would be y by 3 and x by -1. And then our translation second, that'll be 2 to the right. And then just did the mental math to do this. If I multiply y by 3 and x by -1, this will become 0, 3. This will become -1, Then if I move 2 to the right, this will become 2, comma 3, and this will become 1, comma 6. The other thing that we're going to need to do with an exponential graph is we have to figure out what's going to happen to the asymptote. Now, since the asymptote starts at 0, multiplying it by anything won't make a difference, because 0 times 3 is still 0. So even though we're multiplying y by 3, it's still going to be 0. So I made my arrow a little bit longer, because the only thing that's going to affect a horizontal asymptote is if it gets moved up or down. Something that's horizontal, if you move it left and right, it will still stay exactly where it is. So we do not move anything up or down. Our asymptote is going to stay at y equals 0. To draw our graph now. I'll draw it right here. Beside the other one, we can add our asymptote. It has not changed. It's still at y equals 0. We can plug our points in. We have the point 1, comma 6, and 2, comma 3. Connecting those points and going towards the asymptote, this is the shape of my final graph. So the question said, once we've done this, is our final blue graph increasing or decreasing? This one happens to be decreasing. Intercepts. There's no x-intercept, but it looks, because it's going to keep going to the left, there should be a y-intercept. It doesn't show up on my graph, so how do I solve for a y-intercept if it doesn't show up on my graph? I can always algebraically plug in 0 for x. Then you would get 2 squared times 3. 2 squared is 4. 4 times 3 is 12. So our y-intercept is at 0, comma 12. The equation of the asymptote is still at y equals 0. Domain is everything, and the range is bigger than 0. So I'm going to give you a graph. There's some space on page 346. I'm going to give you one to try. Start at the top because we're going to do a few added graphs to the notes here. I would like you to graph y equals -5 times 3 2x plus 4 minus 1. Keep working. I'll put up the answer here so you can see how you do it. first thing you can check is, did you find the corresponding points correct? So labeled all of my stretches and compressions, set up my points and where they're going to end up. Also looked at my asymptote, and it's going to get moved one down. I can now put this information onto a new graph. Asymptote's at -1. I'm going to have a point at -4, -6. And -3.5, -16. And so there is the shape of the final graph. Again, need to label those 2 points to give your scale, and label your asymptote. If you still have room on page 346 and 347, I'd like you to add the following. If not, there is room on page 357. Today we get introduced, some of you for the first time, to a new number. You thought you knew every number that was. The new number that we get introduced to is E. Some of you might be confused and think that's a letter, but it's actually also a number. It's a number like pi, right? On your calculator, there's a pi button. You hit it, you push equals, and it says 3.1415 ... and the numbers keep on going. The number E is like that too. Probably right now I'd say take out your calculator, see if you can find the E button on your calculator. Push enter because we want to figure out what is it equal to. Find the E button, see if you can find the E button on your calculator. 2 point something. That's right. Oh, right? 2.7. Yeah, so it's 2.7. This is as many decimal places as I have memorized. It sure looks like it keeps going with the pattern. You see that 1828, 1828? But no. It's just like pi. It goes on forever without any pattern at any time. Wow. There's no repeating pattern. So it is a number that continues on forever. And it has huge implications for calculus. And so we get introduced here to it because its implications in calculus have to do with exponential graphs. So now you're going to be asked to graph y equals 2 to the x. And it's not hard. It's the same as graphing 2 to the x. The 2 key points you're going to have are 0, 1. And plug in 1, you get 1 comma e. So you estimate it to be at about 2.7. And you would still have an asymptote at y equals 0. And then you'll be asked to graph all of your transformations with an e to the x graph, which, just like before, is exactly the same. You'd have to say, what is my original graph? My original graph is the e to the x. So I have that graph already. What do each of those numbers do? The 3 is going to be a vertical stretch. Multiply your y values by 3. The negative 2 is going to be a horizontal translation, 2 units to the right. And the negative 1 is going to move things 1 down. So you can set up your arrows with your original points. And when doing math with the number e, you would sort of do math just the same way as with pi. If you multiply e by 3, you'd get, this is a hard one in English, 3, which is different than 3 and different than, 3e, 3, hey, woo. All right. So you get 3. So we multiply by 3, and we'd have 1 comma 3. And then you'd have to move things 2 to the right and 1 down. So when you move it 2 to the right, you'd get 3. And when you move it down, 1 down, you'd have 3 minus 1. When I made this question, I don't think I realized how good of a choice it was to choose the number 3. Makes it like 2e just not quite as fun. And your asymptote moves down 1 as well. So when you graph it, 2 comma 2 is easy to graph. Y equals negative 1 as asymptote is easy to graph. And you would have to estimate where is the 3 minus 1 for the y value. So you basically have 3 times 2.7, about 8.4. Minus 1, that is approximately at 7.4. Do that as best as you can. But the shape and all the mathematics is the same. We're just doing it with a new number that's a little bit weird. I could get you to graph y equals pi to the x, which wouldn't be hard. You'd have 0, 1, and 1 comma pi. Okay, questions? I am going to get you to circle our number 10 and 13.